Okay, TAM 210. Here we're talking about the moment of a force about a specific axis. So this is my crude drawing of the tire problem that was done in class last week. And I hope to show that kind of more conceptually what this means when we talk about the force about a specific axis, the moment of a force about a specific axis. So in this problem we had a tire shown by this bad circle here, and a force that was being applied up, right, in the z direction at point A. And point A has components what? It goes in the minus x direction, a distance ax, and then into the positive y direction, a distance ay. And so hopefully you can see that that force with respect to O is going to contribute to two moments, right? Because we have two moment arms acting, one ax and one ay. And so we can calculate what that moment is as ROA cross F. And I'm going to show you where those two moment components come from. Right? So there are two moments, and all that means is that remember, a moment is a vector. And so that means it has components, right? X, Y, and Z, or I, J, K. And that in this case, we have two components that are a part of that net moment. So if we calculate ROA cross F, then what we have is the position vector from O to A, which is minus AX, AY, 0, crossed with the force vector 0, 0, F. So F is pointing up in the positive Z direction. And now we can take the 3×3 determinant of this system, and hopefully you can see or should know right away that you should have everything, the resulting moment, right, is going to be an I and J. The K component will be 0. Why? Because when we fill this determinant in, right here, right, you're going to multiply, the zeros will cancel out. A couple of other terms will cancel out that actually make this not so bad. So if we do the I component, remember we start here and then we do this cross. So we have F times AY, and this is for the I. And of course the opposite side contributes nothing. And then moving on to the J, we're going to cross these two. So this is minus, and then it's a minus AX times F in the J. And then plus in the K. You can see here that these two are not even going to enter the equation, so it's 0K. So this is where those two components come from. So the sum of the moments with respect to O is equal to F AY I hat plus F AX J hat. So the question is, in this problem, which moment component will actually turn the wrench? So notice here that the moment, right, has two components. So I'm going to draw it in the plane. It has a positive I component and a positive J component. So it's somewhere like this, right? It's in the XY plane. This is the total moment axis, and it has components in the J and in the I direction, right? So that's what these moment vectors represent. But only one of these moment vectors is actually going to turn the wrench, right? This direction does not turn the wrench. This is actually going to bend the wrench, right, about the x-axis. So this is not the direction. It's going to be, so I'm drawing up at the top of the video here, it's going to be this moment, right, about the y-axis. So imagine you've got this wrench, you're pulling with the F direction, it's actually going to be in the other direction, right, this way. That's going to turn, and will actually turn the wrench, right, so the wrench main part is right here. So notice only the J component of M will cause the wrench to spin. So what we really want, right, in this question is the moment about the y-axis that really matters. And that's what we mean when we say what is the moment of a force about a specific axis, right? So in this case, this is the total moment, right, vector, the moment axis, but not all of them really matter for our application. So in this case, we want the moment of the force about the y-axis because that's the axis that this is going to spin. So in this example, it's pretty trivial, right? We already know it because we've broken it out into Cartesian components here. But what if the axis you care about isn't so easy, right? So what if it's with respect to some other random axis? And that's the example that we did on Monday in class. But I'm going to follow this through with this current example so you can see in principle what's supposed to happen. So what you need to do is use the dot product. Again, here the example is a little bit trivial. So if we want the moment due to the force about O, but along the y-axis, mathematically this is equal to the moment dot the y-axis itself, which is a unit vector 0, 1, 0. So remember that we can calculate this directly as the additive sum of the components. So what does that mean? So what's our moment vector? It's coming from right here, right? I'm pulling this from right up here at the top. In the I direction, FAY. The next one is FAX. And then we have 0 dotted with 0, 1, 0. Mathematically, we're just going to take, right, the sum of the products. So therefore, MO for the y-axis is equal to just FAX, right? Because these two are just going to be 0. This gives us the FAX, and then of course the 0 and the 0 for the z components. So notice that this is a magnitude. Right? So to express this as a vector, you have to multiply it again by that same axis direction. Right? And that's exactly what we have up above. The moment of y is equal to u. So you take the moment of the force along the axis that you care about, and then to express this as the vector moment, then you need to multiply it by the unit vector of the axis that you're asked about. So this is exactly the moment analog of the dot product questions that ask, what is the force along a specific axis? Right, so here we have magnitude FAX multiplied by vector 0, 1, 0. And so here you're going to have just the J or the Y component. All right, next video coming up will be on couples, and that'll take us through.